So today I am going to take this finite element analysis session, multiphysics analysis using finite element method. So first we'll start with a brief introduction of the finite element analysis. So finite element method or finite element analysis, basically it is an approximate numerical method which is used to solve partial differential equations. So why partial differential equations? Because most of the systems, physical systems, we can model them as a partial differential equation. And in structural analysis and in fluid dynamics analysis, structural or thermal or fluid dynamics, generally we model the system as partial differential equations and we solve them. And another important thing is it is an approximate method, so it is not exact. Okay, so there are basically three methods for solving any problems. First is analytical method, second is experimental, and third one is numerical methods. So analytical and experimental methods, they have certain limitations, and to overcome that, these numerical methods we use. So for analytical method, it is very accurate, but it is limited to only simple problems, simple loading, simple boundary conditions, simple geometry. So if we have any complex system, then we cannot perform analytical analysis. Similarly, experimental techniques we can perform for any type of complex problems, uh, but the cost involved in experimental techniques, that is very high. And another thing is we have very limited outputs if we want to analyze any system. For different outputs we need to change our setup completely, so again it involves more cost. So that's why we go for numerical methods. So to overcome the limitations of analytical and experimental techniques, we use numerical methods. And finite element method, finite difference method, finite volume method, these are most commonly used numerical methods. So today I am going to focus on this finite element method, and later when we will start multiphysics simulation, then I will use the coupled FEM FBM method for solving the two-way coupled problem. These are some of the fields in which we can employ the finite element method. Like we can perform stress, strain, and deformation analysis of structures, various types of structures, which is isotropic, orthotropic, composites, or any kind of material behavior. We can perform a stress analysis, deformation analysis. We can solve fluid flow and heat transfer problems. We can model various manufacturing processes and analyze the variables on those processes like casting, welding, cutting. These manufacturing processes we can model. We can characterize materials also, like for any material we use generally the tensile test, compression test, torsion test, some fundamental test for getting its properties for different loading conditions. So those virtual experiments we can perform using FEM, and we can characterize any material. We can perform multi-body dynamic analysis or rigid body dynamic analysis, in which our major focus is to get the velocity, acceleration, and displacement of rigid bodies. In multi-body dynamics, we have rigid bodies as well as the deformable bodies. So in deformable bodies, we will analyze stresses and strains, but in rigid bodies, we will focus on the uh, acceleration, velocity, and also the loads at the joint loads, we can say. And very important thing is vibration response of structures. So different types of vibration analysis we can perform, like response under harmonic load, response under random vibration, response under deterministic time varying load, modal analysis. So these kind of vibration response we can obtain. And we can perform coupled physics, coupled field analysis, multiphysics simulations like fluid structure interaction, fluid thermal structure interaction. This FTSI stands for fluid thermal structure interaction, piezoelectric and electromagnetic. So these kind of coupled field analysis we can perform. So these are some of the application fields that are used. FEM is used in these fields generally. These are some of the examples. Nice contour plots. You can see this is analysis of pen blade, the analysis of truss structure, and this is the engine housing, the aeroplane. its engine and gear train mechanism. So a lot of structural analysis we can done. And actually this finite element analysis is 50-60 years old field. So almost you can find in all aspects of engineering analysis, people have done this use this finite element analysis. So what is the finite element procedure, the fundamental procedure? So here we can see this first left side image. This is the geometric model of deployable fin. So deployable means it has a revolute joint, and this is a fin of a missile. Okay, so this is the fin is used for generating the aerodynamic lift and for controlling its path. So this fin structure is given to us, geometric modeling, and we have this fins governing differential equations and boundary conditions. Now we want to analyze this structure, and we want to get the deformation, stresses, strains, and other energy, other quantities. So these are right side. You can see this is the result for directional deformation, the fin at different locations. So in between, we have this step, that is finite element modeling and analysis. So this is our input, this is our output. And so how do we convert this input in this output is we transform these governing differential equations into system of algebraic equations. And this form is the form of the algebraic equation is this Ku is equal to F. K is a stiffness matrix, or it is representing the system's property, we can say. U is the uh, primary variable, which is unknown. So this is the vector. Actually, we call it in a structural mechanics, we call it displacement vector. This K is a stiffness matrix, and this F is the force vector. So this is the external forces or loads or external agents which are working on the system. So we convert the differential equation in this form of governing equation. So we discretize the system. Here you can see that the solid model is there, and we discretize the solid geometry in small elements, and we obtain this K, U, and F for individual elements, and then we sum up those elements and solve for this U. Okay, using Gauss elimination or any linear equation solver techniques, and then we get this primary variable. So primary variable means U we will get, and then we solve for another in another state, that is called post processing. And in post processing we get our secondary variables like stresses, strains we want to calculate, which is calculated from this U. So this is the fundamental procedure. One more thing is that finite element analysis, here you can see, is formulation plus implementation. So formulation means we do formulation for these individual elements. We derive the element stiffness matrix, element force matrix, and we decide how many nodes should be there, what degrees of freedom should be there. So these all the things. These are formulation part. And implementation, we need not to worry about these elements. Like we are using ANSYS or Abacus or any commercially available tool or open source tool, which are developed earlier. So we just use those tools, and formulation is already done. So when we want to perform some analysis, so user level, you can say, is this implementation, and for formulation we need more expertise and more theoretical background. So these are the steps for using finite element method for solving any problem. First is geometric modeling. So basically we specify the domain for the partial differential equation. Then second is material assignment. So system property we define. Then third one is element selection and discretization. So there are a lot of elements in ANSYS also. So many elements are there. So we have to select what is best suitable element type for our problem, and then we will discretize our whole domain using that element. So we can select like 1D, 2D, or 3D elements based on our problem. Based on our physics, we can select the structural elements, thermal elements, coupled field elements, like that. based on the domain complexities also we can select. Like if your domain is very complex, then we go for this tetrahedral elements. If it is simple, then we go for rectangular or hexahedral elements, like that. Elements depends on linear or non-linear problems also. If we have a non-linear system, non-linear material properties or non-linear context, then we will use different sets of elements. If we have linear system, then we will use different elements. And then the next step is element formulation, which comes under that the finite element formulation. So we use weighted residual method or energy method, which is called functional method, for getting the element we can say element matrices. So element stiffness matrix, element force vectors, and shape functions, all those things. So, but here we when we are using ANSYS, we did not to do this element formulation thing. It is already there. So we have to just use that element and discretize our whole domain. Then we calculate the element matrices. So we calculate for each individual. Let's say there are 10 elements. So we will calculate we will find that matrix element matrix for individual 10 elements. Then we will assemble those individual elements in a global matrix. So we'll get a big global matrix. So that is assembly to the global matrices. Then we apply the boundary conditions on those assembled matrix, and then we solve for the primary unknowns and then secondary unknowns, which is called post processing. And then we analyze the results. So whatever analysis we have performed, so we are getting some physical meaning of those results, or the results are completely opposite to our expectations, like that. So we analyze the results, and then we iterate these steps. We again, if the results are as per our expectations, if we are able to match the results with some experiments, then it is okay. Otherwise, we repeat these process from the starting point. So we see if some geometric feature we are missing or some material aspect we are missing, like that. So, can we use some different elements? Okay, so number of grid independence study we perform. So we use different grid size. So different number of elements will be there. Like that, we perform again this whole step, and we analyze our system. So here, left side, we can see different types of elements. When we are solving a 2D problem, then the major elements are triangular and rectangular. 1D elements are also there, like beam element, bar element. So those are used to solve the one-dimensional problem. And here these are three-dimensional elements like tetrahedral, pyramidal, hexahedral, prismatic, like that. This is a example of how that finite element formulation is done. So how that governing equation, which we saw Ku is equal to F, or K delta is equal to F, how we derive that governing equation, and how our elemental quantities are derived. Okay, so I will not explain this in detail. I will just go through it. This is from textbook Finite Element Analysis by P. Sheshu. P. Sheshu is our IIT Bombay professor only, Mechanical Engineering Department. So we start with the definition of stress for deriving the equations, and then we calculate this strain energy. This strain energy is sigma x into d epsilon x. Sigma is stress and epsilon is strain. So this approach is energy method. There is a separate approach for deriving the same equation, that is called weighted residual or weak form. Okay, so this energy method is a simple method. That weighted residual is more involved, Galerkin's method, like that. So this energy method, what we do, we calculate the total potential of the system. Okay, so the total potential should be constant. So total potential consists of two parts. First is strain energy, and second one is the potential energy of the external forces. So that total potential should be constant with respect to or change in the primary variable. So first we calculate du, like u, strain energy we are calculating here from stress and strain in terms of. Again, we will calculate this potential of external forces v. So here this q is the distributed load, p is the point load. since we are considering here one-dimensional problem. And this total potential phi p is u plus v. Okay. So we differentiate this total potential with respect to our primary variable, and we set it to 0, and then we derive that governing equations. So for deriving the generic form of finite element method, we assume this alpha is equal to n into delta A. This n is very important quantity. It is called shape functions. Okay. So shape functions are basically interpolation function. This delta E is the vector of nodal quantities or nodal displacement vector, we say, because here we are solving structural problem. So this delta we will consider as a displacement vector. In thermal or fluid flow problem, this may change. So this is basically vector of primary variable. We call that primary variable u. So this so in finite element analysis, what we do first, we calculate all our primary variables, secondary variables, all those things at the nodes. So nodes, what is node? These, when we select any element, so the intersection of these two lines, these points we can see, these are called nodes. So when we solve this finite element problem through this whole procedure, first we get the variables at these nodes. We convert this continuous system, any continuous system, in discrete system, and we obtain our results at these discrete points, not a continuous function. It is not a continuous function, it is a discrete function. So we'll get here, 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 and then we use some interpolation function to get the quantities at anywhere inside this element. So that interpolation function is called this n shape function. Okay. This shape function also depends on elements. For different elements, different problems, we have different shape functions. And this alpha is the quantity at any location inside element. So here you can see this n for this. This is a bar element, linear bar element, which has two nodes, node 1 and node 2. And at each node, we have 1 degree of freedom. So at node 1, we have 1 degree of freedom, that is u1. Here we have 1 degree of freedom, that is u2. That is the definition of a bar element. An element having two nodes and 1 degree of freedom at each node. Okay. So here this shape function is for this bar element, n is equal to. Then using this strain displacement relationship, this epsilon is equal to b into delta E, we obtain this strain matrices. So again, this B is an important matrix that is called strain displacement relationship matrix. And we substitute this epsilon and stresses and shape functions, all those things, in that U strain energy and in V the potential of external forces, and then we sum them UE and VE. So E here represents the elemental strain energy, elemental potential energy. We sum them and we get total potential energy pi PE for individual element. Okay, so from here this KE is derived, B transpose B E8 dx. It is basically dV, like that for 3D problem. Since it is 1D problem, we have here A dx. So here this KE is called the element stiffness matrix, and some portion of this is taken as FE. This is called element force vector. So this is a big expression for that. And so when we substitute KE and FE here in pi p, we get this kind of expression for pi PE elemental. Then we sum it for all the elements. So pi p, total pi p is summation of pi p for all the elements, and we get this expression. Here this K is the global stiffness matrix, which I explained earlier. So summation of all the elemental stiffness matrix. F is, it is not like sum. It is there is some standard procedure for assembly. The F is force vector, again the sum of all the element force vectors. And then we differentiate this total potential pi p with respect to our delta primary variable displacement vector and set it to 0, and we get this K delta is equal to F equation. Okay, so this is the derivation procedure for this K delta is equal to F governing equation, and this governing equation is for static structural problem. Linear also we should say, because here this K is independent of the deformation. when this K stiffness matrix depends on the deformation, then we call it as a nonlinear finite element analysis, nonlinear formulation. Okay. So here this next section, they have given the derivation of the shape functions and those matrices for the 1D bar element. So here you can see this U, then delta is U1, U2, and shape functions, strain, then B, this matrix. So here you can see how we are converting the differential form, integral form in a matrix form. Okay. So here it is B transpose B E A dx. So here we substitute B here, perform the integration, then we get this expression, this matrix. Okay, so this is a fundamental procedure for performing the finite element formulation. It is not analysis, it is the formulation, first step. Then whatever we are deriving here, so this element matrix KE, you can see this element matrix we'll use for all the elements. So that is the implementation part. So this was the brief introduction of the finite element procedure, method, and some governing equations. So if you have any doubt, you can ask. Then we will start the problem solving. Okay, any doubt? Okay, good. So no doubt. So I will start the problem. So everyone, you please start your ANSYS Workbench, and we'll start solving the problems.
But does ANSYS Workbench doesn't work in IITB guest Wi-Fi because wireless is not working.
For ANSYS
It's
guest one,
showing me that license error again and again when I'm starting it.
I don't know about that, but it works with guest login also.
Or else you can connect VPN, Namrita. I'm working on that.
For others, is it working? Okay, so we will start with this problem. This first problem is a simple beam problem. So we will solve for shear force and bending moment diagram. So how many of you know shear force and bending moment diagram?
Yeah, we know. I know.
Everyone knows? Okay, so shear force and bending moment diagrams are basically diagrams for analysis of any beam. So in beams, we calculate what is the shear force, okay, along the cross section, and what is the bending moment acting. So these are first force and moment calculation. Based on this force and moment calculation, we obtain the stresses like bending stresses. So we will calculate both shear force, bending moment, and then bending stress. So here, for solving this, we will use beam elements, which I mentioned earlier, with the rectangular cross section. So beam elements are basically one-dimensional element, line element, and which has 2 degrees of freedom at each node. Sorry, 3, like ux, uy, and rotation about the axis. Okay, so we will use that beam element. So we will here first drag static structural. Then we will go to geometry. We'll open in design modeler, new design modeler geometry.
Hi, can you be a bit slow because here things are lagging.
Okay. So this is the dimensions. It has a 2.5 meter, then 3 meter, then 2 meter different span. here at point B, it has a hinge joint, and at point D, it has a roller support. And at point A and C, we have a vertical force of 20 kilonewton and 40 kilonewton. So if in previous two sessions you are aware of how to do geometric modeling, then you can start modeling. How we will model this system is, we will have three different sections, A, B, B, C, and C, D, and we will join them through the key points. Okay, and then we will apply the loads and supports at those locations. So you can start. If you know, don't wait for me. So here, this is design modeler. So we will select this XY plane and select sketch. We'll go to sketching. We'll select line, and then we will draw line. So we will start from this point. 1, then 2, and then 3. This will be H1. Then we'll go to dimensions and select general. This will be H1, be H2, and this will be H3. Okay. Now here we can modify this H1, H2, and H3. So what was H1, H2, H3? 2.5 meter, 3 meter, and 2 meter. So I think these two lines are not, and I will delete this. Okay, so we have our three line elements, three different sections. So any doubt till here? We have to just draw lines, that's it, nothing else. Then we will go to concept, lines from sketches, and we will select this is sketch 1, apply, and generate. Now we have one line body. So how do we generate any body? We first create a sketch in plane. Then using that sketch, we generate line or plane or line or plane we surface we generate, and then we extrude that for creating any 3D body. Okay, so we have our this line body. We'll also go to concept cross section, and we will insert this rectangular. Okay, here we can specify B and H. So here we can see the H is 250 mm and B is 80 mm.
B is how much?
H is 250 mm, 0.25 meters, and B is 80 mm, 0.08. Okay, everyone done till this point? Then we will go to Workbench and open this model. We should also save this at each stage. So we will save the project. Okay, so we'll go to model. So this is the basic window outline of the ANSYS mechanical and the static structural, transient structural, harmonic, any analysis which uses that ANSYS APDL solver. ANSYS mechanical will have similar kind of GUI. So here we will select this line body and we will assign the cross section rectangular one, and we will keep all other settings as it is. So here we change actually material also, but we need not to worry about material here. Why? Because we are just performing the stress analysis or shear force and bending moment diagram. Material comes into picture whenever we want to relate stress and strain. Now we'll go to mesh and we'll simply generate the mesh. So this is the default mesh, which I think it is sufficient. So here you can see this finite thickness also. So if you want to switch it off, then you can go to display and this option we will switch off. So now here we can see this is a line element with different nodes. Okay. Then we will go to static structure. And so what we have to do now, we have to, so till this point, what steps we have done? First, we have done geometric modeling, then material selection, material structural steel we have assigned, all that is not required. Then cross section, again geometric modeling, coordinate systems already defined, mesh we have generated. So generating mesh means now here we are not specifying the what element type it should be and how much node should be, all those things. Why? Because this ANSYS mechanical, it automatically based on your geometry, it select the element and discretize the structure. Here you can specify number of elements, like here element size is default, you can change it to any element size. So number of elements that you can select or element size you can change, but what type of element it is selecting, that you cannot change. So for changing that, actually we should go here in geometry tab, line body, and here different options are there. What like you can see here, model type is beam already by default. So when you will change this, okay, pipe, laying truss, then the element type again it will be changed. But here we will select this beam only. So up to meshing, we have completed element selection and element formulation. All those things are done. Now our next step is to define boundary conditions. So boundary conditions and loadings. So we will insert.
Excuse me, will you please wait because we are running parallelly. It's very difficult to cope up with your speed right for me.
Oh, okay, okay. So up to meshing, is it done?
No, not yet.
Okay.
I did this rectangular body thing I did. After that, what to do? I don't.
So this ANSYS mechanical you have opened.
Yeah, ANSYS mechanical. No, I am in design modeler right now.
Okay, you're in design modeler. So in design modeler, you have done this rectangular cross section you have selected. Okay.
Yeah, that I did.
Okay, so now you can see here this one part, one body, line body is there.
Yeah.
Okay, so you go to
And
workbench.
in sketch, rectangle one is there, line one is there.
Uh-huh.
Then
Then you
where
go
to go?
to workbench and open the model. This model cell of that static structure. You double click on
Okay.
that, and then this mechanical will be opened.
Okay. So I can close design model, right now.
You can close or you can keep it open right now, because if any geometric changes is required, then you can do directly. Otherwise, opening that will take again some time. Actually, here in ITB, we have sufficient number of licenses. That's why we can open several windows here. But limited number of licenses are there, then we need to close the windows.
So I got into the project thing model.
Now you are in ANSYS mechanical window.
Yeah.
Okay. So the first is project. So inside project there is model, and inside model there is geometry. Okay, geometry tree option is there.
Yeah.
Then in geometry, when you will click, you will see your line body.
Yeah.
Now in your line body, you select the cross section, which is yellow there. Na? In cross section, you select the whatever cross section we defined, that rectangular cross section.
Okay.
Okay.
Done.
Then next, go to mesh, because these other things we have done already. Material modeling is done. The cross section we have defined. Coordinate system we have defined. So go to mesh and right click and generate mesh. So we are not changing any settings of the mesh also, meshing also.
Okay, I got it. Done.
Okay, so everyone completed till this point. If anyone is left, then please let me know. Okay, then we will go to next option is static structural, and here in the menu bar where this file, home, these things are there, there is environment. So you can click on that environment.
Static structure.
Then on top of the window, you can see menu bar, file, home, environment.
Okay, fine.
In environment, you click. Now here you can see in the ribbon, all kinds of loads and supports are given here. Okay, so these loads, you can see a lot of loads options are there. Force and moment is directly here. Support also, when you will click, you will see a lot of support, remote displacement, compression only, cylindrical, like that supports are there, and fixed friction, these are also given. So what we have to do is at 2.5 meter, we have to apply this hinge. So hinge means what? It can rotate about this point, but it cannot move in X or Y direction. Okay.
Yeah.
So we will insert here, we'll go to support and we will insert remote displacement. And here in now we have to select the point at which we want to apply that remote displacement. So here we will select this vertex option. Can you see this?
Just a minute. Okay.
Here in this top ribbon, you will select point, and then at this point, when you will move your mouse cursor, you will see whenever it will reach to that point location, it will show like this.
Okay.
So you select that point and hit apply. Okay, now that vertex is selected, and we have to specify. Sorry.
Just give a minute. We'll do that.
We have to select that vertex using this vertex selection option
Yeah,
here.
that I checked that. First, remote displacement we have to apply, then we have to select the vertex, right?
Yes. So when you will select this remote displacement, you can see here in details panel. Here, okay, outline also, let me explain once. So here left side you can see this is tree outline. Okay, whatever option we will insert, we will do here only. Whatever boundary condition we want to apply, force, settings, everything. And whenever we will select any options here, we will see details of that just here in left bottom corner. Okay, so like here we have selected remote displacement. Now we can see details of remote displacement. When we will select analysis settings, we will see details of analysis settings like that. And here we have that window where whatever we will do here, we will see that graphically. So first we will select this remote displacement, and remote displacement here in details we can see scope option is there. Then within scope there is geometry option. Okay.
Yeah.
So in geometry, when you will click, we have to specify the geometry at what location we want to, or at what point, or at what line we want to apply this remote displacement. Because for applying boundary condition, we need location where we want to apply. So we have to select that point. So for selecting that point, here on top of this ribbon, we can select this vertex selection filter, and we will select that, and then here we will hit apply.
Okay.
Done till this point?
Just. Are you there in that group, ANSYS workshop? I'll share the photo how it is looking for mine.
Okay, okay. So here in top yellow geometry, you can see geometry and no selection, that is in yellow.
Right.
So click on no selection.
Just a minute. Yeah. Okay.
And cancel two options.
Yeah. Apply. Shall I apply?
Apply.
Okay. Got it.
Now that yellow is gone.
Yes. Yes. Yes.
Okay.
I
So
got
now
it.
bottom you can see again 6 yellow lines are there. So X component, Y component, Z component, and rotations. So what this remote displacement boundary condition do is it connects first it defines remote point. So what is remote point? Remote point is a point which connects all other nodes, and we can apply the rotations also. Like one question you may ask that sir, here we are using one dimensional element, and that element has only u as a degree of freedom. So how we are able to apply this rotation? So like in 3D bodies also you can apply rotation. So this you can say as a trick also. Whenever your system has only linear motion degrees of freedom, but still you want to apply rotation, then you can use this remote displacement boundary condition. So here in remote displacement, you have to specify what is the displacement in 3 direction and rotation about those 3 axes. So for our problem, it is in XY plane. So we will select X0, Y0.
Do you mean like we can give any support system by defining the degrees of freedom in any direction? We are using remote displacement thing rather than directly going for fixed or roller or anything automatic. So, right?
Yeah, correct. So here X, Y, and Z translation will be stopped. We will give it to 0. Rotation about X, that also is 0. Rotation about Y, that is also 0. And rotation about Z, that is free. So this whole beam can rotate about this Z axis at this point. Okay.
How you gave that? Can you show once again?
So here you just enter the values in all those
Zero.
yellow lines.
Directly, I should put 0 because I was in workbench and I didn't.
Here only in remote displacement, when you will select, you will see the details of remote displacement, and then in yellow lines, there you can see X component, Y component, Z component.
Yes, yes.
So you enter the values there on right side.
Okay. Got it.
So there you can see all free options will be there. So if you will specify, because all cannot be free, if all is free, all degrees of freedom, then it will be rigid body motion, and ANSYS cannot handle rigid body motion. Okay, because for this particular software, it is ANSYS structure.
So
now,
rotation Z is only there.
only rotation Z is free, so you don't change that rotation Z. Remaining all will be 0. So that is our first remote displacement. Again, we will apply another remote displacement at another location. So at the end, I think it was at end or where? At point C. So we will again insert from the ribbon, we will insert remote displacement 2, and then we will select the another point here, and again we will in geometry tab we will hit apply. Again that vertex is selected and applied. And next we will, now here you can see there is a ruler support. So what is the ruler support? Oh, it is at D, sorry. So ruler support means it cannot move in vertical direction only, y direction, but it can move in x direction, and also it can rotate about the z axis. So we will change this vertex. I selected here, this is at the end. Okay. Now again x we will keep free translation along x, y we will set 0, z we will set 0, rotation x 0, rotation y 0, and rotation z will be free. So everyone done till this point?
No, just wait for 2 minutes.
Okay, okay. Now done. Okay, let me tell this step again. You go to again environment. In menu bar, you select environment, and there you go to supports. In supports, when you will select this drop down, there is a remote displacement option. You click on that remote displacement. Then one remote displacement with question mark will be inserted. Then you go to geometry, and there you will see that option for selecting apply and cancel. Now you go to that vertex selection option, and you select that end vertex. And then
Something's wrong with my answer. Unable to view geometry, unable to get model.
what?
Something is wrong going with ANSYS, I guess, for mine. I'm unable to open model again and geometry as well. Okay, I'll just see.
Can you share a screenshot? Okay.
Mhm.
What about others? Have you done? So there is a problem with your workbench setup. What you can do, you just drag another static structural
Okay.
and connect the geometry option to this new geometry.
Okay.
Done?
I did. Then I will go for yeah, I did.
Then you can delete that
Sure.
connection and try to open that new model.
Okay. Mm. Okay. So I have to create mesh and all right again.
Yes, you have to create.
First geometry, then line body, apply.
Go to line body, then apply that cross section and go to mesh and generate mesh. Right click and generate. Done?
Just to make them bring apply mesh.
Hmm.
Yeah, meshing is done. Then I have to go static structural.
Ah,
Then I have environment, support, remote displacement,
ah.
node, vertex.
Okay, then accept rotation
First,
Z.
yeah,
Everyone
first I have to apply or first I have to select.
first select, then click apply.
Okay.
So X, Y, Z components displacement will be 0.
0.
Rotation X, rotation Y also 0. Rotation Z will be free.
Mm.
Then similarly insert again another remote displacement.
And I'll do just a minute.
Uh,
So this is done. Again, I have to go and again I have to select the remote displacement 2.
Then select the end vertex, right end vertex.
Hmm.
And for that, your X component will be free and rotation Z will be free.
Just a minute.
Okay, done?
Yeah, done.
Now you select the vertex where we want to apply the force. So force is at the first left vertex.
Hmm.
Then right click, insert, force.
Right. Insert, force. Okay, red color thing came.
Then here you see the magnitude 0.
Yes. I have
So
to
above that there is defined by option. Okay. So
click
you
to
click on
define.
that vector option and the drop down is there. You select that as a components. Then now you
Yeah,
can see
no,
X,
just a minute.
Y components and three yellow lines. Now we have to apply Y force, Y component of force. So X and Z will be 0. Then how much force is here? 20 kilonewton force is there downward. So we will go here in Y, we will apply minus 20,000.
Y
Okay.
is minus 20,000.
Because here
You
you
meant
can see right side in window or XYZ coordinates are Y is up, X direction is right side, positive. So for downward, we have to apply minus 20,000.
Okay, got it.
Now you can see here one arrow pointing downward.
Yes, yes.
Again, we have to apply a 40 kilonewton load at point C. So we'll select that vertex. Again, right click, insert, and force.
What point we are applying at C?
C point.
Okay. Insert force.
And again, defined by components and magnitude minus 40,000.
In Y direction.
Okay.
Done.
So now you can see all the question mark have gone from this project tree. You can see whenever you complete one step, that question mark will be gone. If you will miss any of the step, like let me suppress this to force suppress. Now you can see question mark. It means that you cannot run the simulation until you have solved that problem. So here you are missing the load. If you will not apply any load, what it will solve. So you have to apply any load. If you will apply a single load and if you will apply a single support, it means now your problem is well defined and you can solve. Okay, now you click solve.
Just a minute. What if like it is going for underweight? Like beam, we have created a beam, right? We have given rectangular cross section, and we have defined material. So it does have their own self weight also. So it can have displacement based on that or something like that, right? Even if we are not giving any force, under self weight, it should deform.
So for self weight, we
Hmm.
have to select here in environment only. When you will select a static structure, there is environment. Okay, an environment where we inserted that remote displacement. There you can see inertial. Now in inertial tab, we have options acceleration, standard earth gravity, like that. So until and unless we will apply that standard earth gravity, it will not consider the weight of the structure.
Okay. It
So
is
here,
just considered as a line body right now.
yes, yes. So here in this problem, actually, they have not considered that self weight. So that's why I was also not considering there.
Yeah, when we do in like SOM, we don't consider that, but it's a general doubt which I asked.
So actually, what happens? This load due to gravity that affects those structures which are very large in dimensions. Okay, so heavy structure. So for those, like for small components, if we want to perform the analysis, we can neglect the effect due to the weight. Why? Because other loads are the effect of other loads are very significant as compared to the effect of weight in small structures. It is not like weight will not be there. Weight will be there. You can take that also, but it will unnecessarily add complexities and more computational cost. Uh, and when you will leave that, it will not have significant effect. Okay, so in small structures, we leave that load due to the gravitational acceleration.
Yeah.
Okay, so now everyone done up to this point.
Yes.
Now we will click solve. So here you can right click and click solve, or in top environment ribbon also there is solve option. So you can click on that.
Solve.
Okay, solved.
Not enough constraints appear to be applied. Something.
You can neglect that, avoid that message. That is actually warning. So warning you can avoid.
So, is there any option to change the sign conventions also in the ANSYS anyway?
Sign convention actually you cannot change. By default, it is X, Y, Z direction is defined in this direction only. You
Okay.
can change your body. Like
Okay.
slide modeler or a space flame, you can change orientation of your body. Like if you want to orient your longitudinal axis along Y, so you can rotate your body along Y.
Okay.
So now you go to the solution. Now you can see the right tick mark there. So in solution, when you will go, then the ribbon where environment option, environment menu was there. Now solution menu is there.
Formation is
Can you see here on the top?
yes. I am getting the solution information. Not only.
No, no, not solution information. You select solution. One
Okay.
above that
I
is.
got.
So now here you can see environment is gone and now solution is there. And a lot of these options are there now for solution: deformation, strain, stress, energy, damage, all those things. Okay, so now in a deformation, you click that small arrow drop down and select this total.
Okay.
Now in total, right click and evaluate or retrieve, whatever option is there.
Okay. I got the colorful diagram in this.
Now you can see that how this beam is deforming.
Hmm.
So now here in graph, in middle, bottom side, the graph small, this window is there.
Hmm.
So there is play button. So you can click that play. So you will see that deformation, how it is happening.
Yeah.
Okay. So now what is our objective? To plot that shear force and bending moment diagram. So again, we will, now here you go to solution in tree outline. Then right click, insert, and in beam results, you will select the shear moment diagram.
From
Okay.
where you got that
Again,
solution?
solution, then in solution, right click, insert is
Okay.
there. Then in insert, you see deformation, contact tool, bolt tool. Go down, down, and you can see beam results.
Just a minute.
In okay, in beam results, there is shear moment diagram. Solution in tree outline. I am telling. Left side जो outline है ना वहाँ पे.
Yeah.
Right click, insert, then beam results, and then shear moment diagram.
Again, that mechanical thing, model thing get gone from mine.
What happened?
Same issue which happened, no? We copied again geometry.
Oh, I think it's something
Something
to do with your system.
might be. So we are
Okay.
doing everything on model only, right? Till now.
Yes, yes, model only. No,
I
actually,
do.
it is not model only. When you will see here in Workbench, we in model was up to the meshing only. Now the setup option, that is also right. See? So
Yeah,
setup also.
everything is right. Results is also right for me, right? In this.
So actually, when we open model, so all these other four cells, na, model, setup, solution, and results, all these four are within this window only.
Okay.
Okay,
Mm-hmm.
you need not to go there again and again.
Okay. Just
So for results also there is a right tick. Now we will
yes.
insert in solution. We will insert this beam results and this shear moment diagram. Now for that, again we can say there is one question mark. Can you see this question mark? And yellow lines are there, path and geometry. Again we have to select. One minute. Hello, am I audible? Hello.
Amit, you are audible.
Okay, okay. So sorry, I had an urgent call. Okay, now here the total shear moment diagram we have to insert. Then here we can see two yellow lines. One is path and another one is for geometry. So geometry you can see all line bodies, but path we have to select. So we will go to here again outline tree in model. We will right click in model. There is insert and there is a construction geometry option and there is path. Can you locate it? So we will click this path. Now again there is one construction geometry tree option is there and inside that there is path. Okay, now we have to select. Here you can see in start 3 yellow lines are there and below that location is there and again apply and cancel 2 buttons are there. So we will select this again vertex and we will select this first vertex left one and we will click apply. And in end bottom of that end is there, again we will click on the location, click to change option is there, we will click on that and we will again select this vertex and right vertex we will select and we will hit apply. Okay, now you can see there is one path created 1 to 2. So for this path x is equal to 0 will be at 1 and you can see arrow direction. So from 1 to 2 the x will change. Everyone created that path. So what we will do, we will go to model, in tree outline, we will go to model, then right click, insert, and then construction geometry, and there is path. Okay, now for path, we have to select 2 points. So first start point and end point. So we'll go to location, click to change, and we will select the 2 vertices. First left, we will select for start, and right, we will select for end. Done up to this point. Then we will go to this total shear moment diagram, and in path when we will go, we will see here the drop down option, and we will select that path which we have defined. That option is not working. Okay, let me check 1 minute. Okay, we will see that in 1 minute. Let me insert another option. Okay, so we will insert another result, like in solution, we will right click, insert, and then beam tool. And then we will click on this beam tool option. Okay, now on that beam tool, there are three options: direct stress, minimum combined stress, maximum combined stress. So you just right click on that and evaluate. So now here we can see that minimum and maximum stress value. Okay, so this maximum combined stress, we will look and we can see the location of the maximum stress, so which is here at the support, at roller support and at the hinge location, and that maximum value is 1.875 E8. So here it is in Pascal, units are in Pascal. In this graphical window we can see the value, and so here we can change the unit also. In left side corner you can see here the metric option you can see. So when you click on this arrow, upside arrow, so you will see this systems. So we will select this metric mmkg, third option. Now it is 187 MPa. Okay, so what was the stress here? So it was 60 MPa. So I think we have missed something. Let me check. Okay, 1 minute. Let me stop my sharing. Okay, I'm again sharing my screen. Okay, can you see it? So we have made two mistakes here. Why results are not matching? Actually, one mistake. This in rectangular option, this B and H, this we have not defined correctly, I think. So we will change this. Let's say this B is 250 and H is 80. And now let's solve this problem. Okay, so now here we can see that our maximum combined stress is 60 MPa. So which is the result here, the 60 MPa. Actually, by definition, the orientation of the thickness and BH height we should select properly. Okay. Am I audible?
Audible.
Okay. So next, so this stress now we can see. Again, we have to plot the shear force and bending moment diagram, like what we can see here in this left side, sorry, right side results. We can see that shear force and bending moment diagram is here, bottom side. So we will plot that. So the same procedure is there. Only one change is that what path which we are defining. Now, we selected 2 points. So here actually for SFD and BMD, we should not select define it through point. So we will insert another path. Okay, now here you can see that first option is in details path type. So we will change this path type to edge. From 2 points to edge we will change, and then we will select this edges. So in geometry you can see yellow line geometry, no selection. So we will click on no selection. Now there is a apply and cancel option. Now we will select this edge selection filter. So already it is there. Now we have to select the 3 lines, okay, line segments. So 1, 2 and 3. So using control, you can select all the 3. You click on first and press control and select second and third. Now we will hit apply. So here we can see now our path is defined from 1 to 2, and this path is named as path 2 in my case. In your case, it will be path. You can change its name also. You can rename it and you can give it any name. Okay. Now we were inserting here. Let me delete this. So now we will right click in solution, in tree outline, solution, then insert, then beam results, and same shear moment diagram. We will click, and again you can see the 2 yellow lines. So in path we will select whatever path we defined. So path 1, path 2 in my case, and now this all line bodies, it is by default selected. Now here in type we can select total shear moment diagram, or we have options directional shear moment diagram for Vy and Vz. Okay, so our x is the longitudinal axis. So we have 2 axes y and z in which we can calculate our shear forces. So here, since we have applied our load in y direction, so we will select this Vy. Vy is your shear force in y direction. So second option we will select, and then we will evaluate all results. Right click and evaluate all results. So here in graphical window, you can see your shear force and bending moment diagrams. So this first one is Y shear force. The second one is bending moment, and this third one is displacement diagram. Okay. So here you can see the diagram, shear force and bending moment diagram, same 50 kilonewton meter maximum moment is there. So here also minus 5.7 Newton millimeter. Okay, this is same. When we will change units, we will see that. Yeah. Okay, so everyone done up to this point? So this was our first problem for calculating shear force, bending moment, and displacement diagram, and also for calculating bending stresses. Now, if anyone has a doubt or not completed, please let me know. Everyone done? Namrata?
It is not working, so I'll just check it on break. What is the issue? Because again, I'm doing it's not working at all. The model is opening for me.
Okay. One thing you can try, you save it very frequently. You save, so whenever it will crash, I think it will start from there. You can try that, because in some systems, I also have seen this kind of problem. What about others? Please give me some feedback so that I will be able to know whether you are getting it or not, or you have stuck somewhere. So we can start from there.
I understood I can do, I guess. If I discuss, I'll ask you after a break, if at all, once this is sorted.
Others like Sagar, Shweta, Avasthi, Sri Kumar. So everyone has joined online from their room.
Yeah.
Okay.
Today everyone is online only.
Okay. 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 So we will start with our next problem. So let me summarize what we have done. So we started with geometry. We opened this design modeler. We selected the XY plane and inserted one sketch from here. Then we draw 3 lines. Okay. We gave dimension to those 3 lines, and then we selected this concept and line from sketches. So we created line body. So initially we created sketches. Now from sketches we have to create body. So from that line sketch we created on line body, and also we inserted one rectangular cross section, and we assigned the height and width of the rectangular cross section. Then we went to this workbench and opened the model. So that model will start the ANSYS mechanical application window. Then in application mechanical application window, we will go to outline, left side outline tree, and we will start one by one changing all the settings, and making wherever we will see the question mark, we will make that as a right tick. We will change some settings so that it is a right tick. Now first we selected that in model we selected that geometry, and in geometry line body we assigned the model type as beam, then the material as static as structural steel. Then we went to mesh option, then we created default mesh by right clicking and generate selection. Then we went to static structural. In environment we selected the remote displacement at 2 points and force at 2 points, and then we solved the problem. So after solving it, we selected the solution option in the tree, and in solution we inserted a few results like total deformation, this beam tool, and this directional shear moment diagram. So for shear moment diagram we need one path. So for path we again went to this model, right click, insert construction geometry, and in construction geometry we created path by selecting edges. The path created from selecting points that will not work for this shear moment diagram. So we selected that edge, and from that edge we created our path, and then that path we selected in our shear moment diagram. And also we don't want the total shear moment diagram, we want directional shear moment diagram, and directional in y direction, vy direction. So v represents shear force, so in vy direction we created our shear moment diagram. And also in beam tool we see this maximum and minimum combined stresses. So our maximum stress is this 60 MPa. Okay, so this was the first problem of solving the shear force bending moment diagram. Then next we will solve this 2D problem. So first problem was 1D problem, 1D beam element, one dimensional. Why? Because the element was one dimensional beam element. Okay, now we will select 2D. Also we selected that line body, so that's why it is one dimensional problem. Now we will select our 2D plane stress analysis. So two dimensional geometry will be there, and we will discretize that also using two dimensional element. So particle element we will use for discretizing this geometry. So let's first understand what is the problem, then we will start solving it. So for a plate, infinite plate, rectangular plate with a hole, okay, a small hole at the middle of this. So it creates a stress concentration at this discontinuity. This hole is a discontinuity, and whatever stresses will be here at the end, that stress means force upon area. So whatever stresses will be here, there will be much higher stresses as compared to this nominal stress at this discontinuity location. So that is called stress concentration. And the stress concentration we defined, that stress concentration factor is defined by peak stress at the discontinuity location. Here you can see this is the discontinuity location. So here there will be peak stress divided by nominal stress. So there will be nominal stress based on the cross section. So that is called nominal stress. So this stress concentration factor is sigma peak by sigma nominal. So for the case of infinite plate, here at right side you can see this sigma nominal is equal to sigma applied. Okay, so we will calculate our sigma applied here at this location, because this area of this hole or notch is very small as compared to the the continuous area. So that's why the area will be A net will be approximately equal to A, and therefore this stress sigma nominal will be same. Okay, so the KT for this discontinuous plate we will get from this formula. Okay, so here this is the circular hole. From theory, we know that the stress concentration factor for an elliptical hole in an infinite plate is calculated using this formula. KT is equal to 1 plus 2 A by B. So A is the major axis, half of the major axis, and B is half of the minor axis. So when this ellipse instead of this elliptical hole, if we have circular hole, then A is equal to B, and when we will substitute A is equal to B, we will get KT is equal to 3 for this circular hole. Okay, so we will try to solve this problem, and we will try to get this stress concentration factor KT as equal to 3 or nearly equal to 3. Okay, got it? So these are the model details. So we will model this quarter of the plate. So again, now there is a very good option in any finite element or finite volume analysis. That option is called symmetry, that is boundary condition. So whenever our geometry and our load is symmetry about any plane or any axis, then we can create half or quarter of that body, or in axis symmetric bodies we can just create the plane and we can get results for the 3D body. Like, okay, so we will use that symmetric option. So here we can see this plate geometry and loading is symmetric about both axes. When we will cut this from the center, so in y and in x direction, so we can see that this plane and this plane both are symmetric plane. Okay, so we will apply the symmetric boundary condition here, and we will model this quarter of the plate, and then we'll apply our loading is given here. So the horizontal force will apply 5 kilonewton, and material, again, since here we are performing stress analysis, we are not correlating stress with strain, so any material we can select. So by default structural steel is there, so we will keep that structural steel material, and we will use 2D quadrilateral plane stress element with 4 nodes. So here we can see that this is the 2D quadrilateral element and 4 nodes are there. Okay, 1, 2, 3 and 4, and each node will have 2 degrees of freedom, displacement along x and displacement along y. And we can expect a result normal stress of 51 MPa. So this normal stress of 51 MPa will give us the stress concentration factor as 3. So we will close this. Okay, or we can insert here only. SFT. Again, we will drag static structural. Then we will go to geometry. Now we will use a space claim geometric modeler. These are the dimensions of the plate: 100 mm in length direction, 60 mm in width or height direction, and 10 mm is the radius, diameter of the hole. So here we will draw the rectangle. So again first we will draw the whole rectangle, then we can cut it. So we will learn that option also. It is 100, so we will enter 100, then we will press tab button, and here we will give 60, then enter. Okay, now we can see rectangle is created, but it is not symmetric about this x and z axis. So we will select this dimension, and from this z axis we will click first, and then second this one side, and this should be 30. And again we will select this x axis, and then this side, and it should be 50. This length is 100. Okay, now it is symmetric about this x and z axis. Then we will click on this circle, and this is center, and we will draw on circle. The radius is diameter is 10 mm. Okay, and now we will click on this. Everyone done till this point?
So can you just show how you gave the dimension thing? I missed that.
Okay. So here in space claim, you have one advantage. You can do Control Z, Control Y like that, undo, redo. You can do. So for giving dimensions, here in ribbon you can see sketch in menu option, and in ribbon there is dimension here. Okay, so let me do that again. So we will click on this dimension. Now dimension of what we want to do, that object we have to select. So let's say first we want to give dimension of this side, so it is 100 mm. Now we want to specify the distance between the z axis and that side. So we will first click on z axis and then the side, and where we want to place this this letters 16 mm is written, so where we want to, so you can click on any location. So here let's say we click. Now in 16 mm we will click, double click, and we can give any dimension. So here it should be 30. Okay, so 30 mm in this direction, 30 mm in downward direction. Similarly, we want to place this left side from 50 mm from this x-axis. So we will select x-axis, then the side, and in between we can click, or anywhere we can click. Now it is 23 mm, so we will change it to 50. Okay, so now it is at the center. Done. Then we will select this circle. In sketch ribbon, we will select circle. And then we will click at the center where the origin is, and we will drag it, and we will just enter the value. So it should be 10. We will enter 10 and then click enter. Press enter in keyboard. Now this hole is also created. Okay, so now we have completed the sketching part. Now we have to create bodies from the sketch like we did in design modeler. Here also we have to do same thing. We have completed our sketch, and from sketch we have to create bodies, line bodies, surface bodies, solid bodies, like that. So here in bottom we can see this option, return to 3D mode. So when we will click on this return to 3D mode, it will directly create surface from our sketch. Here. Okay. So here the pull option is automatically activated here. You can see this pull option, and some options are here in this window work area. So we will not do anything else because we want to work on the surface body only. So here in structure left side, you can see in structure outline tree, one surface is created. So this is the surface. So press escape so that pull option is deactivated. Now we want hole in this circular face because here is also the surface, here is also the surface. So but we want to create a hole. So we will just select that circular part and will press delete. So it will delete that area. And now we have created a plate with hole. So now we want to cut this from the horizontal plane and from the vertical plane, so that the only one quarter should remain there. So what we will do, so here in the menu option, file, sketch, then design. So we'll go to design. Okay, now in ribbon you can see a lot of options are there. So these are for the 3D bodies. We can modify 3D bodies using these options. So here 3D bodies or any bodies, line bodies, surface body, like that. When design, we will select this split option is there. You can see combine, big combine option is there, and here is a split option, split body, then a split and project. So this split option is for splitting edge and surfaces. This split body is for splitting any 3D body using any cutting plane. So here we will use this split option because we want to split this surface. And first we will select this surface. Then now we have to select any point. So at that point, from that point, it will draw two horizontal and vertical line, and it will cut this surface. So we will select at okay. So here we will. You can see whenever we are placing this point, we have two dimensions there. Okay. So horizontal dimension we will make it as 50, and then vertical we can keep anything. Then we will press enter. Now it has divided this surface in 4 parts: 1, 2, 3, and 4. You can see 1, 2, 3, and 4. Okay. Similar thing we will do for splitting this part also. So we will again select split, then we will select this face, and again we want to split the face. But now from we will split from this horizontal axis. So this sorry, this vertical axis. So this horizontal dimension we can keep anything. We will press tab. Now here we can see that vertical, this option is there. 1 minute. Okay, we will specify both x and y values. We'll go to design, split, and select this face, and we will give this horizontal value as 50, and this vertical value as 30. Okay, now it is directly cut in 4 equal parts. We'll press escape. Now you are out of that split mode. Now here you can see there's 4 options. Now we will just keep one and delete all others. So we'll select this and delete, delete, and delete. Okay. So now our geometric modeling is completed. Now we will go to again workbench and then model. So we'll double click and then ANSYS mechanical window will open. So everyone completed this geometric modeling. Yeah, hello, am I audible?
Yes, you're audible.
Okay. So now after completing this geometric modeling, we will go to mechanical tab, again model, then here in model geometry, then this surface. Now we have to specify thickness, okay, here, and again the material. So thickness we will give as 5 mm, so 0.005, or you can change the unit system from meter to millimeter. Okay. Now you see, when we have not specified this thickness, the yellow line was there and the question mark was there in geometry and in the surface. So now when we specified that thickness, so now we can see that a green right tick mark is there. So it means our this geometric specification step is completed. So here we can select, see what other options are there. It's dimensions are there. So 2D, 3D like that. So here we will select the 2D, and in axisymmetric option we will select plane stress. Oh, but the problem here is we have not specified properties. One more problem is there. Whenever we want to model any 2D body, now we have to do it in XY plane only. So we will keep it as 3D and we'll just solve the surface and let's see if it is working or not. So we'll keep this as a 3D only and we'll solve this problem. Again, here we have to select the material. So by default material is structural steel. So we'll keep that. And here the model type is shell because we have selected this body. So it is shell type. Now we will click on mesh, will generate. So here you can see the mesh. So if we want to switch off this 3D, we can go to display and with this thick cells and beams, we'll click. And now we can see this 3D mesh. So now this mesh is
Hello. Like, can we add a custom material in ANSYS, like bamboo or something?
yes, we
Can we add the properties like
any materials properties? Okay, let me show you how we can do that. So here in engineering data, so actually next session will be on composite material modeling only. So I will cover that also, but let me briefly describe that also here. So here in engineering data tab, now we have so many materials and we can create our own material. So let's say we want to create any random new material, let's say mat. So we have to give its name here. Below structural steel, there is one blank space. So we will give name of the material here. Let's say name is mat. Now you can see one question mark is there. and the material is here. Now we have to specify what properties we want to give. So let's say if we want to perform thermal analysis, then we have to give the thermal conductivity, the specific heat, the thermal expansion coefficient of the material. Okay. For general elastic analysis, we have to give the Young's modulus, the Poisson's ratio, like that. So here we will select that material, and in left side tools, you can see here a lot of material properties options are there. So we want to specify linear elastic. So we will click that. Now here we have isotropic elasticity, orthotropic elasticity, and isotropic also. So we can select anything like if you want to model bamboo, then it is orthotropic elasticity. So you have to double click on that. Now here you can see in bottom side properties of outline row of the material mat. Here you can see again the orthotropic elasticity. Now when you will expand this orthotropic elasticity, you have to specify 9 constants. So for defining orthotropic materials, we need 9 constants. Young's modulus in 3 directions, Poisson's 3 Poisson's ratio, and 3 shear modulus. Okay. If we add linear elastic isotropy, so I will delete this orthotropic, and I will double click on this isotropic elasticity. Now here isotropic elasticity is added. When I will expand it, I have to specify 2 constants. One is Young's modulus and Poisson's ratio. Okay. So like that. If you want to add plastic model, then here this plasticity option is there. So different types of plasticity: bilinear, isotropic, multilinear, nonlinear. Different options are there for plasticity. If you want to add thermal, then so some properties you are not able to see here. Why? Because you can see top there is a filter engineering data. This option is selected here. Okay. So what this filter engineering data option do? It filter the properties based on your type of analysis. So here we have selected static structural. So in a static structural, automatically it assumed that you are not going to use the thermal properties. You are not going to use other electrical properties. So it disabled those things. So when you will click this filter, then again some more options are added. Now here you can see all these different properties, whatever is available in ANSYS. And then here we can see this thermal option. So we can give isotropic thermal or any property here, specific heat, okay, specific CV, CP. So this is the procedure for defining any user-defined material here. One more thing is here you can also specify the material property as a function of temperature. Okay, you see when I'm selecting this Young's modulus, okay, and we can also insert the density. So the density will be in physical properties here. So density and second coefficient of thermal expansion, like the damping factor, viscosity, these things. So let's say I want to specify any material property as a function of temperature. So I will click on that. Here, let's say Young's modulus is there. And here I can give constant value. Or I can give here in right side, you can see there is one small window, temperature and Young's modulus value. So you can here give the temperature dependent properties. Okay. And also a lot of inbuilt material properties are there in ANSYS. So to access them, what you have to do, you select here below this engineering data menu or tab, there is engineering data sources. So you click on this engineering data sources, and now you can see various types of inbuilt material here. So ANSYS Granta materials and general materials, additive manufacturing, like some composite materials are there. So you can click on any. So these are actually groups. These are not materials. These are groups. Like you will, when you will click on general materials, now you will see a lot of materials here. So outline of general materials. So gray cast iron, magnesium alloys, polythene, stainless steel, titanium alloy, a lot of things. Similarly, when you select this ANSYS Granta material data, again, some huge collection of materials brass, air, cast iron, copper, a lot of metals you can see. Now here, whatever material you want to add to your simulation, you have to click on this plus. Here you can see the material name, and here this add option is there, plus. So whenever you will click this plus, this material is added to your analysis. So let's say we have this general material, we want to add this stainless steel. Okay, so we will click on this plus. So this magnesium alloy, will click on this plus. Okay. So you can see these properties of these materials. So stainless steel, what properties are included in this stainless steel? So here in bottom you can see the properties. Density, it is already there. Isotropic elasticity is there. Isotropic secant coefficient of thermal expansion is there. Tensile yield strength, compressive yield strength, specific heat. A lot of things are here already inbuilt. Tensile strength. So these, all these properties you need not to define U values. It is, you can directly use these values. Now when you will again click this engineering data source, right now it is blue. When you will click it again, it will become gray, and here you can see those added materials. So again, you have to resolve these question marks. Until and unless you have this question mark, you cannot solve further. So we will delete this. Now magnesium alloy, stainless steel, structural steel. So any of these material you can use in your ANSYS mechanical. Now we will go to project, and here when we will update, okay, refresh it, not update. So here this there are three symbols. Now you know the meanings of these symbols. If it is right tick, green right, means you have done completed that step. If it is yellow, this yellow tick is there, you have to update it. And if this green refresh, these arrows, rotating arrows are there, then you have to right click and refresh it. Whenever you will refresh it, it will take whatever changes you will do in previous steps. Okay, now question mark is there, so means you have to complete this step. It is not completed. So now we will again go to model. So it is directly open. Now here in materials you can see whatever materials we added. This is structural steel, stainless steel, magnesium alloy. These are here. Okay, so we can select any material for any body. Here we have just one body, so we are structural steel we have selected. We can change this. So here in arrow, when we will click, we can select magnesium alloy. Okay, if we have multiple 5, 6 or a number of geometries, we can define individual different materials for different geometries. Okay, so got it, how we can create custom materials and modify materials. Any doubt on this? Okay, so we will go ahead. Now we have done this, we will go to mesh. Now this mesh is not proper, okay, because it is not able to capture this circular arc properly. It has just 3 segments, so it is not meshed properly. We will get an error for this. So what we will do, we will right click, and this clear generated data, we will create new mesh. So we will select this edge first, this circular arc, by selecting this edge selection on the top, and then here when we will select this, in the top you can see where the menu bars is there, home, and then mesh option is there. Earlier we have seen environment, we have seen solution, now it is mesh. Since we are in mesh tab, so this menu is changed to mesh. Now here we can see solve, insert, update, generate, and this sizing option is there. So we'll click on this sizing. Now when we click here, you can see in the tree outline, the edge sizing is created here. Why edge sizing? Because we selected edge. If we will click on this sizing without selecting anything, it will just give sizing and then question mark is there. Now we have to select edges or lines or surface or body, anything. We can give any kind of sizing here. Face sizing, body sizing, edge sizing, like that. Okay. So we have selected edge sizing here. Now in the details of the edge sizing, here you can see type of element size. So here this type means we can give element size at that particular edge, or when we will click here, so in drop down we can see number of divisions. So we will use this, and we can divide this arc into a number of divisions only. So we will divide it into 20 elements or 20 segments. Okay. Now similar thing we will do for this side and this side also. So we will select this side and insert sizing. Now it is element size is bigger. We will select for this also number of divisions.
Am I audible?
Hello.
Can you hear me?
Yeah. Am I audible?
Yeah, you are. Actually, can you just little bit elaborate about this edge sizing, because I didn't get the concept.
Okay, sizing means what we saw now that mesh. So the initial that default mesh generated, the element size was very big. Okay, so we want to refine the mesh. We want further refinement. Why? Because that arc it was not able to capture properly. Okay, let me show that again and generate. Now here you can see this arc, it is creating only 3 lines instead of that arc. So what will happen when we want to approximate any arc? We should draw small lines. Then we can create approximately that arc, circular arc. So similarly, here it is just creating 3 lines for that arc. So that's why it is not properly capturing the arc. So what we want to do, we want to refine the element size here. Okay. So that's why for that refinement, what we are doing, we are inserting this edge sizing. So in edge sizing, what we have done, we selected this edge at whatever location we want to locally refine the mesh. We select that edge, and now we will give how we want to refine. We can give size there, like one element should be of this much size, or we can give number of divisions. So this total segment will be divided into 20 parts, 50 parts, like that. So we can give number of divisions also. See here we selected this number of divisions and we want to divide it in 20 small segments. So then we give it 20. Okay, got it? Then next we will insert again an edge sizing for this edge, for this left vertical edge. And here also we will give number of divisions, and we will give for this also let's say 20 division. And similar thing for this also, sizing, we'll select that edge, click on sizing, again edge sizing is inserted. In details, again we will change this type to number of divisions, and we will give number of divisions as 20. Now let's see how the mesh looks like. Now here you can see the mesh is refined near this wall or near this curved surface. Okay, and also it is refined in this along this location also, along this line, vertical and horizontal. But still what is happening here is, when you will see from this mid location, your element size is constant throughout this end. Similarly in this vertical axis, in this vertical line, from this your mid or before that also, here you have uniform element size. So what is actually the common practice in finite element analysis is, we don't want to create a uniform mesh. Why? Because your stresses will be higher or gradients will be higher at some locations, and it will not be that much significant in other locations. So we want a biased mesh. We want to refine the mesh only where it is required locally. because when we will remesh the whole body with small elements, the number of elements will be too large and it will take a lot of time for solving. So that's why we want the concept of local refinement. So local refinement means where the discontinuity is there, or wherever we want the refinement, at that particular location only we will refine. So here we don't want this homogeneous or uniform mesh. So what we will do in this edge sizing for this particular lines, vertical and horizontal, here you can see in details there is option of bias type. Okay, so right now by default it is no bias. Now we will change this bias type no bias to this first one. Okay, and we will give a bias factor of 5. Now you can see how, or let's is 10. Now you can see how this mesh will look like. It is very refined at one location and gradually it is increasing with 1.2 sorry, with 10 bias factor it is increasing. So but it is increasing in the opposite direction. We don't want refinement here away from the notch, we want refinement near the notch. So what we'll do, we will change this bias type, this second option. Now it is in proper direction. Similar thing we will do for this horizontal edge also. Bias type, we will select this first option and then we will give the bias factor as 10. Again it is opposite, so we can change it to second. One more option is there, we can refine in both the direction, like at the center it will be larger and both the direction the refinement will be there. So but here we don't want this kind of refinement, so we are okay with this. Okay, we can increase this number of divisions little higher, so let's say 30, and for this also 30. Oh sorry, change again, 30. Okay, now we will see how the mesh look like. Now here you can see the refinement is gradually increasing towards the far edge, you can see, and more refinement is there near the this notch, circular notch. Okay, so now this mesh looks proper. We can further refine if we want to refine using this whole face sizing option, but it is not required right now. Later we can study refinement. Now meshing part is also completed. So everyone done till this point? So next we will again go to a static structure. Now you can see again your menu is changed to environment. In environment we have to specify the support and loads. So we will select this edge. In this edge and in this horizontal edge we want to specify symmetry. So there are two ways to specify symmetry. One is directly we can select symmetry option here. Another one is you can restrict the displacement in this normal direction. So we can specify a displacement here, zero displacement in the z direction, and for this surface zero displacement in the x direction. So that is one way. Or else what we can do, we can go to model here, right click, insert, and then symmetry. Okay, so this symmetry object is inserted in this tree. Now we will right click again in this symmetry object, will insert and symmetry region. So now you can see this edge is red now. So it has selected that edge and symmetry it has assigned. Now we have to specify the direction of the symmetry. So the direction should be normal to this edge. So that axis is z axis. Here we can see in the bottom right corner, the z axis is the normal direction to this edge. So here the symmetry normal we will select as z axis. Okay, so now we have specified symmetry for this. Similar thing we will do for this edge also. We will select this edge. Now we will go to this symmetry object, right click, insert symmetry region. Now symmetry region 2 is created. Again we can see this red line, and then for this the direction is x, so this x is proper. Okay, no need to change it. Okay, so now we have specified the symmetry option. So symmetry means what? This it will mirror this uh, surface about that axis. Okay, so once it will mirror about this axis, so half will be created, then that half it will mirror about that horizontal axis, and the full domain will be created. Now we have to insert the force. So we will select this edge, and here in the top ribbon environment we have this force option. We will click on this force, and again we will define by select these components, and we'll specify the z value, because here the normal is z direction. Okay, so the z value, what was 5 Newton, I think, 5 kilonewton, 5 kilonewton. So this is 5, sorry, 5,000. Now this 5,000 load is in which direction? Positive z direction, but we want it in opposite, away from the normal, away from the body, so it will be minus 5,000. Okay, so now we can see here minus 5,000. But one more thing is here, whenever it is very important point, whenever we want to apply this symmetry boundary condition, we must take care that our geometry, not only our geometry needs to be symmetric, but that load condition should also be symmetric. If loading is unsymmetric and geometry is symmetric, then we cannot use this symmetry boundary condition. Okay, so what does it mean? If I am applying 5,000 Newton here, what it will do? It will apply 5,000 Newton in this opposite direction also, towards left. Okay, in another half, and in bottom half also, what it will do? It will apply 5,000 Newton. So how much force will be there total? 10,000 Newton. Getting my point? So the actual value, when we are modeling the symmetry, when we are slicing the body, we are considering here half of the body, so we should divide the load also by half, so it will be minus 2500. So now what will happen? 2500 here, and 2500 will act on bottom side also, so total load will be 5,000 Newton. Okay, getting my point? Now here we can see that all question marks have gone, and we have these yellow marks for tick marks for update. So we'll just click in analysis settings, no need to change anything, we'll just solve this. So we have some issues here. Symmetry we have given in x direction, in z direction. Okay, so that error which we are getting, that pivot point error, so that error is because of we are getting that rigid body motion at somewhere. So if rigid body motion is there, then it will not be able to solve. So for arresting that rigid body motion, I applied this displacement in XYZ 0 here. So actually the problem might be because here we are solving that 2D problem in 3D solver. So I will show you how we can solve this 2D problem in 2D solver only. So the problem might be because of that. Okay, but now that problem is gone. So we have inserted one displacement for this particular edge, and we applied XYZ components as 0. Okay, now we will insert and see the deformation and stresses. Insert stresses equivalent 1 minus the stress. Sorry, we will see the normal stress, because that stress concentration factor we calculate on normal stress. So here we will insert this normal stress. 1 minus stress also we can check. Now we will evaluate all results. Now here you can see that how deformation is happening and how these stresses are there. So here the deformation is maximum. So actually this deformation which we are seeing maximum at this point, at the top right corner, it should be maximum in this whole line. Okay, in this whole region it should be maximum, the deformation should be maximum. So what we can do, this displacement which we applied in this whole line, what it is doing, it is arresting this deformation in this direction also. So we can this Z option we can keep it free. Okay, now let's see. Okay, now you can see this deformation plot, and this is the normal stress. So here we can see okay, one more thing, whenever we are seeing these results now, here in top menu, this result option is there, and in this result option, when we create in solution, we will have this solution options. A lot of solutions are there. Whenever we'll select any result like normal stress or total deformation, we have result option here. Okay, now in this,
Could you please explain that how you resolve that rigid body problem? Because you gave Z as 0, right? Like, so if there any load is acting here.
sorry, your voice is breaking. What you asked? Can you repeat?
Could you please explain that how you resolve that problem, error actually? Because you get Z axis as 0, right?
Uh-huh.
Like, so if you give Z axis as 0, is there any force acting right now?
No. Here I gave this displacement. Okay. Actually, I have already defined symmetry, so it should not give that error. But in that error, why? Because we are solving the 3D problem here. As I showed here, here in surface body, we have this dimension in 3D. So that's why we are getting this problem. If we will solve it on 2D, that problem will not be there. Now again, if that problem is there, what we can do, we can restrict any node or any line. Even if we will select any node also, then also it will not give that error. So what I did, I selected this bottom line and I inserted a displacement object here, displacement boundary condition. Okay, so you select this edge, and here in environment there is option of displacement. So I click displacement. So whenever you will select displacement, you will have only three components, x, y, z displacement. But when you select that remote displacement which we used earlier, you will have also three rotations options. So here we can select anything. Since there is no rotation, we can assign them to 0, or directly we can select displacement. But in previous beam problem, we needed rotations also because of that hinge location and the rolling supports. So that's why rotation was important there for beam problem. Here rotation is not important. So we can directly select this displacement, and now in this displacement we changed it, defined by two components. Okay, and now in x, y, z directions I keep x as free, y as free, and I restricted the z direction. I kept z free and I provided x and y component 0. Okay, so now rigid body motion there will be no error for that. Now I solved, and then this. So what will happen if you will restrict this z also? It means this whole this line, it will not move, but in actual practice what will happen, whenever you will apply a force on this right side edge, this edge will move completely. Okay, but when we will fix z for this axis, it will fix at this location also, this corner also. So this corner will not move, but about that whole body will start rotating. Shear deformation will be there. So that's why I freed this z component. Got it?
Okay.
So now we can see the total deformation contours and this normal stress values. So I was telling about these result options in this menu bar. So here we have this scaling option. So if deformation is very small, like here, what is the deformation? You can see it is 0.01 mm. But when you will run the animation, you can see significant deformation. But 0.01 deformation is very small. You cannot see that through your eyes. So here actually it is scaled up deformation. You can scale up at any extent you want. So here in this top set, this drop down option, we can scale it. The one is true scale. So when you will click on true scale, you will just see the contours changing. The deformation is negligible. Now you can scale to proper visualize in what direction it is deforming. So 0.5x auto scale, 2 times auto scale, like that we can select. So now we can see the deformed shape properly. This option is used when there is very small deformation or very large deformation case also. If very large deformation is there, it will go out of your window. You cannot see that. So that's why we scale down that deformation. So this is one important option for visualizing results. Another option is this contours. So here we can see contour bands. You can do smooth contours also. So now it is a smooth coloring here. Okay. So iso lines only you can see, the contour lines will be visible like that. See here, the contour lines are visible on that solid domain. Another option is this edges. Here you can see. So in edges, we can right now we can see all the elements also over the contours. If we don't want to see this, then we can select no wireframe. Now here we can just see the contours. If we want to select this show undeformed wireframe, so this is like that. So initially our body was like this black line, and after deformation it is becoming like its present shape. Okay, so now we can see our normal stress. I will switch this off, no wireframe. Now here you can see this stress concentration. So away from this discontinuity, away from this circular notch, the stresses are uniform. Okay, but at the location of this discontinuity, we can see very significant rise in the stress. So this red zone we can see here. So that is called the stress concentration. Now there is one task for you right now. I think 12:30 is already over, so we will go for lunch. The session was up to 12:30 now. Abhishek?
Yeah, it was till 12:30.
Okay, so what we will do, I will stop here, and there is one task for you, small task. You calculate what is the stress at this location, that nominal stress. Okay, So what will be the nominal stress? Force upon area. So force we are applying. So at this location also you calculate, and at this free location away from this notch, this yellow region, here also you calculate force upon area. So force, 5,000 we are applying, and area, actual geometry, not for this half geometry. You can calculate for half. Then if you will calculate for half, then take force and area both half. If you will take for full, then force and area of full. So force upon area at this location and force upon area at this discontinuity location. Okay, you calculate this, and we will try to match the results whether we are getting same or not after the lunch. So this was the second problem. Okay, any doubt on this? Okay, so no doubts, then we will stop here and we will meet after lunch. Okay, I will stop sharing my screen. Okay, so we will meet after lunch. Thank you.